In this video, we're going to find the eigenfunctions of our angular momentum operators. So in the last video, what we found was that if we took our operators, which were L squared, and acted on our function, which we sort of suggestively put ML, we found that this would have the eigenvalue h bar squared times L plus 1. And then this would be multiplied by our eigenfunction here. And then we also looked at the z component of our angular momentum acting on our function and found that we had the eigenvalue h bar m times our eigenfunction. So now what we're going to do is sort of find what these operators are and then find out, in fact, that this eigenfunction is just the spherical harmonics. And so I took my lazy approach this time and just took pictures right out of the Griffiths textbook. And so here it says first we rewrite our angular momentum operators in spherical coordinates, and the del operator here, which is the gradient, is equal to all this stuff here in spherical coordinates. And so this is in the r direction, this is in the theta, and then the phi direction. And so our vector here is just equal to the length of r, or the radius of the circle, times the direction of the vector in the r direction. And so from this we have our big L, which is our L operator, is equal to all this stuff here, which just came right from what we got up here, and then putting the r and r hat in here. But as we see, the r hat cross r hat, so the cross product of the r direction with the r direction is equal to 0. The cross product of the r direction with theta is equal to phi, and the cross product of r hat with phi is equal to negative theta. This says to look at figure 4.1, which was a ways back, but it's just telling us, if you take the cross product of the direction in the r direction with the theta direction, then you get the phi direction. You get a vector in the phi direction. And same if you take the cross product of the vector in the r direction with the phi direction, you get the negative theta direction. And so from this we end up with this, because that first part here cancels out because that's equal to 0. And so we just end up with our phi here being replaced for that, and then our minus theta being replaced for that. Then we put the unit vectors theta and phi back into the Cartesian components. And so now each of these two things here are just sort of being replaced with these two things here, and so we get the minus sine of phi plus cosine of phi, and then over here down here we get the cosine theta times cosine phi plus cosine theta times sine phi. And so if we simplify this, then in our Lx direction we have this, and in the Ly direction we have this, but we care about this Lz operator because that's one of these one of the two operators up here that we are using. And so that is our LZ operator right here. Uh, we should also need the raising and lowering operators. So remember that was the L plus and L minus, which was defined as this. And so we end up getting this long thing here. And you can see why I just took pictures out of the book, because it'd be kind of boring to just sit here watching me rewrite all these sines and cosines and cotangents and stuff over and over again. But since we have cosine of phi plus or minus I sine of phi, this thing right here and this thing right here can both be turned into this right here, an E plus or an E minus I times phi. And so we end up with this sort of more simple looking thing here. And if we multiply the raising and the lowering operator, so that's essentially just taking the plus version of this and then multiplying it by the minus version of that. So this e to the plus minus I phi is going to get canceled out. Then we're just essentially going to do the FOIL method on this, and it gives us this right here. And so our L squared, if you remember from the previous video, our L squared had this in it. And so when we combine all those things together, we end up with this right here. All right, and now we're in a position to determine our function. It's an eigenfunction of L squared with the eigenvalue h bar squared times L plus 1. And so that's what we have here. And he says this is precisely the angular equation that we obtained by doing the previous method, which was the analytical method. And he says to go to equation 4.18, which I copied right here. And this looks a little bit different because this one right here is essentially this one, but divided through by sine squared to get rid of that sine squared theta on that side. So it divides through by the sine squared there. And so that's how we end up with a 1 over sine squared right here, and why this sine gets canceled out. We end up with a single one in the denominator there. But yes, it is the same function that we had from the analytic method. And then with the LZ, the eigenvalue mh bar is this. And they said that this is the azimuthal equation 4.21, which I took a picture of and put right here. And once again, it looks different. And the other thing to notice from this one is this doesn't have the h bars there, and this other one does not have the h bars either. But it's essentially this one here is just like taking the square of everything here, just squaring everything here, so that m is squared. Then this is made into the second derivative, and then that minus I will go away if you square it and become positive. That's why this is positive right here. And so the take-home message, and the reason I didn't want to belabor this too much, is that we end up getting the same functions. And so these are the theta and the phi functions for the spherical harmonics. So remember, the spherical harmonics was what we got. So our spherical harmonics, which was a function of theta and a function of phi, draw that a little bit better, a function of phi, after we did the separation of variables, which so we had that sort of large theta that was a function of theta times our large phi, which I think looks something like this. That's a function of phi. And so this one up here was our theta, and this one over here was our phi. And so we end up just getting the two uh, equations from the separation of variables that then become the spherical harmonics. And so that, like I said, is pretty much the take-home message of this video. And in the next video, we'll start looking a little bit more at spin. So I've already made some videos on spin that was taking a little bit higher look at them, or not as like sort of deep in the weeds. But in the next few videos, we're going to find out how we can get spin from all of these things. And the thing to remember was that, like in our previous video, we found that our L could take on half integers, even though in our quantum numbers what we have is L being equal to 0, 1, 2, and so on, and our M being equal to minus L all the way up to positive L. But we can have half integer L's, and that will come in when we start looking at spin. But anyway, like I said, the take-home message is this, that using this algebraic or operator method, we end up getting the same equations as we got from the analytic method. And the functions here, the spherical harmonics, are the eigenfunctions of our angular momentum operators, and the L and the M fall out of the eigenvalues that are associated with these angular momentum operators. And so anyway, like I said, I don't want to belabor the point too much. I hope you found this video helpful, and I will see you in the next video.